Okay, hello everyone. In this video, I'm going to show you how to use MidasGen to create a three-dimensional truss model and do the design for both tension and the compression members. So here, as you can see on the screen, a few weeks ago, we used this cantilever truss as an example for tension member design. So now we're going to use the same example for compression member design. So we have already calculated the truss load, the dead load, and the slow load on each interior, such as the joint B and C joints over here, and the exterior joints A and D. So we apply the dead load and the slow load separately, and then I'm going to show you how to do load combination and use MidasGen to analyze this truss and to do structural design, steel structural design. Okay, let's open your MidasGen and create a new project. Open a new project. Okay. Okay, so as soon as we open a new project over here, we can create the truss model. So now instead of creating a two-dimensional truss model, we will create a three-dimensional truss model. So we will create as the truss plane in the X and the Z direction, and the axis perpendicular to the plane of the truss will be Y. So remember that. So now let's create a truss type. So we'll use three-dimensional, and everything here. Make sure you use the correct unit system here too. So everything here. Let's check the unit system firstly. Unit system. So everything is in inches and kips. Okay. So now we're gonna create the three-dimensional truss. So we start from, we could start from the loads, right? So we'll create X and the Z plane in the create nodes. So we will have X loads in the 1, 2, 3, 4. We will have four loads at the bottom chord. So each has a X increment equal to 10 feet. So that's 120 inches here. So number of times that's equal to 4. And then we have the increment is 120. Oh, coordinates, that's the start point. Huh? So distance increments 120. So we could wait for, let's see whether we can show any joint here. Show you that. Okay, so if okay, actually we were able to create 1, 2, 3, 4, 5, right? So actually we just need to multiply by 3 times. Let's save the truss design example. This is the truss design example here, and looks like we can just go ahead and delete the truss number, the load number 5. We do not need it. Select it. Go ahead, select the delete it. So then we recreate more loads on top, right? We will from 1, 2, 3, 1, 2, 3 over there. We create more nodes. So the first one would be we have the z-axis, so that's 3 feet, so 36 inches. And the distance we have 10 feet distance over here. and Z. So each time we decrease the Z by one foot. So that's minus 12. So now let's see whether how many we have. 1, 2, 3. We only need 2 here. So we were able to create the node 5, 6, and 7. Yeah, the 2. So every time we decrease that by 12 inches, that's by 1 foot. 1 foot. 3, 2, 1. Okay, by 1 foot. It's correct. So then we can just create element. So we can collect each of them, and so make sure we use trusses. Trusses here, so we can just create the element one by one. And vertical ones. Do we have any vertical as a support? And another one as the support. And then we have the diagonal ones. So we are done with the creation of the geometry here. So we save it, and now then we assign the properties. So we would like to have WT for the bottom and the top chords, and for the vertical ones, we're going to use single angles, and then diagonal ones we use single angles. So basically, we could use 4 different types of shapes here. So first thing, let's create a material. So we will use A36 for all steel. A36. That's STM database A36. So that's a steel we're gonna use, and then we create sections. So here we're gonna use the automatic section name. So we will not use any custom user defined name, because when we do design, we will say the automatic name would have some benefits here, because every time when we change the size, the name will be changed by the program. So we will have the WT for the top chord. So WT, the top chord, section name, we use a WT here. So we don't know which WT would work, so probably we can start from the lightest there. So this is the WT that we're gonna use for the top chord. So we click apply. We have a WT. So then we will have the second one. So probably slightly larger, WT3 for the top chord. And we will have angles for the vertical member. Vertical, we could start from the lightest one. That's the type 3, and then we will have another one, type 4. So probably slightly larger, the diagonal ones. Okay, so now we have already created 4 different types of sections here, and then we're gonna assign the sections for different members here. So that's when we close it. And then we need we change the properties to go back to the element. And so we want to use the WT2 for the bottom. So the steel, that's the same. We just want to change the section ID. So we want WT2 for the bottom. So we're going to select the bottom ones. Okay, all bottom ones are selected. To apply. So we can also show the section name to make sure we make it correct. As you can see here, the bottom is already WT. So then we want the top is slightly larger. So we select the, we're going to use the W. That we would assume that we could, yeah, so you press the control button so that you can do multiple selection here. Okay, we selected the top, then we apply. Everything has already been changed to WT3. Now let's go vertical. So vertical, we're gonna use AL2. So select first one. Let's control. Second one. Third one. Gonna use WL2. Apply. Everything has already been changed to L2. Then we got to the diagonal ones. We're gonna use L3. This one. Oh no. Okay. L3. Okay. Gonna change this to L3. Okay. So now we use the 4 different types of shapes for different types of members. So bottom, top, vertical, and the diagonal ones. So we better save it. Save it. So next step, when we are done with the section properties, and then we go to the boundary. And then first thing, then let's check whether we use the correct material. Say for WT, let's say what material we have used. It's not showing here, and that's okay. We can show the materials too, to make sure everything is A36. Okay. Oh, everything is A36. Okay, good. Okay. So let's save it, and then we apply boundary conditions. So you can check this is a 3-dimensional truss. So be careful anytime when you have 3-dimensional truss. So we wanted to, top we have a pane, and so X and Z is restrained, and bottom we have a zoner, so only X is restrained. But how about the Y? So we'd better to restrain the Y too. We just define supports. So on top we have a pane, and so we wanted to restrain X, Z, and the Y too. So if you do not restrain Y, so basically this plane will move in the Y direction. So that's not stable. Just we can pick the node 5. Pick the node 5. The rotation, yeah, we'd better restrain the rotation of X and Z and just keep the Y. So we applied 1. So then we move to the bottom. So bottom, we just we can free the Z direction. Oh no. Yeah, we free the Z direction. Let's pick this one. So that's the boundary condition. And then we can check the boundary condition. Oh no. Yeah, so it's like for node 1, X and Y and Rx and Rz is restrained. And for node 5, we have X, Y, Z, all of them are restrained here. So now we can go back to the model and save the boundary conditions, and then we apply load. Remember the dead load, live load, right? Apply the load, static load cases. We will have the dead load. The dead load is the dead load. So we add the dead load case, and then we have the slow node case. It would be a slow node case. It's better to keep there as a default load cases, because in this case you could use the automatic load combinations later. So we have already created node cases. Now then we will apply the self weight. So you could apply the self weight, and you can, because in our example we have already assumed a self weight and combined to the dead load. So we do not have to apply any self weight here. here we just apply the load node. So firstly we apply the dead load. So dead load is in the direction. So for let's go back to our example for the dead load for the exterior nodes. The total dead load is a 1106.25. So in pounds, that's in pounds. So when that's equal to 1.1, so around the 1.1 kips, and just apply the loads. So minus 1.1 kips. So we pick this one, or no? I just can pick this node, and this node. So that's minus node. So we can show that. We can also show the load values here. If you want to show the load values, you just show the load values. That's minus 1.1. There we. And then we apply the dead load to the intermediate. The interior ones. So we calculate that too, right? So that's equal to everything in the parentheses here. So yeah, we could do a quick calculation. So we have, let's see, use my, that's, we have 12 times 10 feet, oh no, 12 times 10 feet times 12.5 feet plus 106.25 plus 250. So that's about 1,856 pounds. So that's 1.856. We apply dead load. So 1.856 to the interior loads. So we select the interior loads here. Oh no. This one. Press Control. And this one. This one. Okay. So interior loads. Let's apply. Okay. So that's the interior loads. And let's save it. So that's a dead load. And then we go to slow node. Slow node, and for the exterior ones, we calculate the slow as 1.25 kips. 1.25 kips. 5 kips. This one and this one. So we apply. So we applied that. So then for the interior ones, sorry, that's 2.5 kips. 2.5 kips. Into this one and this one. Okay, it's 2.5 kips. 2.5. Let's save it. We have applied all the loads here. So then we can check. And then we better just show the animation view here. We do not need to show the three-dimensional view. So here, let's check our application by showing the dead load. So firstly, we can show the load cases for dead load. Dead load, that's it. Oh. No load. So that's the dead load. That's the dead load in the interior ones will be slightly larger than the exterior ones. And snow load. The interior ones has the load double the exterior ones. So that's it. I think we apply the load correctly. Let's save it. So then we go to analysis. just analyze everything here. Do the analysis, perform analysis. Oh, we see some warnings here. We see some warnings here. Yeah, looks like as the dy may be singular here. Dy may be singular here. Yeah, because we follow the 2, 3, 4, 7, 5. So for those nodes, we did not restrain the dy may be singular. That's okay. We can keep it, and we can just check the results to see whether the axial force makes sense or not. Let's see. The axial force. Let's see. We can just show the values here. We can uncheck the load. Do not need to show the load. We do not need to show the properties here. There's too much information. Show the maximum. That makes sense. So we have a 0 member here. The others looks okay. The slow load. Slow load looks okay. Right? And then so that's the results. We are done with the structural analysis anyway. And then we do design. So before we do design, we better to do node combinations. So we define node combinations for steel. We pick the steel one. We can just create an auto generation. So we will auto generate design by AIC. And make sure you use the correct design code here. So we just click OK. So there are different types of combinations. That's a default one. So probably we can ignore those 4. We can just delete them, select them and delete them. And then the name, we better change the name a little bit so we know which one is which. We just change the name as 1.4D, and just change this as a 1.2D plus 1.2D plus 1.6. So that's all the design. So now we have everything here. Can check our result here. Yeah, 96, 64, and about 32. So that's pretty much very close to what we got from hand calculations anyway. And that's it. So now we go to design. So now we can do design now since we have node and node combinations. Okay, what happened here? Okay, no. Okay, we do node combination. We do the check, make sure we select the AIC because design code is different. So the design code has already been checked. Checked out. That's a newer version, and the stress reduction factor. That's 0.9, 0.9, 0.9, 0.9. So that's 4. And modify steel material. We do not need to do any modification. If you want, you can modify this 36 FY 58 as FU. Do not need to do any modification here. So we have already assigned the sizes there. We can show the sizes here by selecting property shape here. Okay, we can uncheck the results. We don't want to show the results anymore. That's fine. Okay. Can uncheck the results. It's already here. Can show the contour. Probably it would be either. Okay, so now let's go back to the design. We can check. We have the forces already calculated, and let's see whether those members are adequate to carry those forces. Go to design, check. Well, the design check is done. So there is a window, dialog window comes out. Looks like, yeah, not good, not good for the bottom chord is not good. Everything is not good, but we could update our design. So, for example, we can change the top. We can do a search, see which one works better. So W looks like WT5. This one looks better. So we change to W. We change that. That would work. 0.8 something. But we need to update that. I need to update. So we update everything. Update the first one at the top. Okay. The first one is okay. So how about this one? Let's change. Find the bottom one. This one looks like what is the lightest one? W4 looks like that's the lightest one. You just change it. Firstly, close. The same internet. I wanted to change this one. See which one is working. What in WAL.4. That's on this. Probably this is the better one. And we just changed everything. But we wanted to double check, so we want to update. So even we have already changed in this table here, but in the drawing here, everything is still the same. So we need to update. Need to select all of them and replace them. And as soon as we replace them, the design results and analysis will be updated. So we want to reanalysis. And we do recheck. Okay, everything's working now. Everything's working now. So we have to use the bigger size here. Okay, so that's the design here. But when you output, when you show your final results here, you want to show, you cannot give your clients a video showing that how you do the design here. It's better to output a report, such as you could show some graphic report. You can select all of them to see whether I can show the graphic report here. Okay, this graphic report does not have everything here, so that's not good. So how about details? We better to show all the details here. Yeah, so this is a better report. So it gives us so for example, the load factors, how much node for each type of member. So for example, steel code check for material number 1. That's size WT 5/11. So the load is calculated. The maximum load is calculated as 6490. So say that's a compression member at the bottom. So compression member at the bottom because everything here is negative. So that's a required load. So 64, we want to make sure the member can carry, and 64 keeps out the compression and check axial stress. As you can see here, the effective length is given 120 inches. So LY is 120 inches, LZ is 120 inches too. But be careful over here is so for the bottom chord that's in compression, as so one effective length is as default defaultly set as 120 inches. 120. That's true for the in plane buckling, but for the out plane buckling, probably not. So yeah, Midas general does not have a function to change the outer plane effectiveness to the actual ones, so it defaultly gives the effectiveness as the member length. Yeah, this is something Midas needs to update or improve their calculations. Right? So anytime when you use that software, make sure you check all these numbers. So the LY and the Z looks like LY probably correct if we say the LY is the strong axis, but for LA probably that's wrong here. That's wrong here. So yeah, so any calculations such as you can see here, checks axial stress, the K over R is calculated, and then steel code checking. You can calculate the FE, K over R, so that's a inanistic buckling. So it's calculated as a KSI. So the size checked out. So that's a very comprehensive report that you could dig into. So I think you can also do several cycles of changing the sizes to make sure you have the latest design. And after you are done here, you can just save this as a PDF. I think you can just print this as a PDF and save it, such as this is all member design. Save it. Yeah, we can check the actual PDF. And so this PDF gives us the design. You can put your company name, your client, the project name, and everything is here. A lot of details. So that's the design report. You should create for your supervisor or for your peer to review, such as anytime if you have any concerns about the effective lens that you used here, especially for the bottom one. So yeah, I would if I review this report, I would check the effective lens, right, to say whether the correct effective lens is used, because that's very critical for compression members. So you can save it, as you can put any comments here. So that's the design report, I think. So in your project, I expect to see similar report. So I think that's all about this. So then you okay, looks everything is okay. So you can output this screenshot to show the sizes here, and I bundle this with your design report in detail with numbers there. So that everybody else who would like to check your design, they can look at the sizes from this chart, from this screenshot, as well as the numbers that you have output in the PDF file. So I think I think MidasGen is very useful here to steel design, and yeah, but be careful anytime when you have a three-dimensional model, you have to make sure the boundary conditions is correctly applied. Otherwise, you will have a lot of mistakes or a lot of errors and warnings coming out to stop the analysis here. Okay, I think that's all for this one. Thank you. Stop sharing. Gonna see. I'm gonna stop recording.